Okay, so now we know, at least at an intuitive level, what first order rules are. And hopefully I've persuaded you that this is a powerful thing that we would like to be able to induce if we can, but it's probably not going to be that easy, right? It sounds a lot more complicated than what we had before. But of course what we're going to do here, as always, is step by step. We already know how to build rules in the propositional setting. Now what we have to try to do is extend that to the first order setting. Hopefully some things will stay the same and we don't need to mess with those. Some things will change and then we need to deal with those and then we'll have a full algorithm. Okay? And this is exactly what we're going to do here. In particular, we're going to look at something that is actually a fairly old first order rule induction system, but still very popular, and it encapsulates very neatly, many of the basic ideas. Or at least one of the main approaches of learning first order rules. We're actually going to see two main approaches. This is the first one. It's the one that builds directly on what we already know about rule induction. Okay? And Foyle, by the way, again, was also from Ross Quinlan. This great UW alumni that is one of the grand, old people in machine learning. He not only invented ID3 and C4.5, he also invented Foyle, right? Pretty amazing guy. And by the way, Foyle is short for first order inductive learner. This is one of those acronyms that really means something. Unfortunately, I then heard people proposing, calling their algorithm shrink wrap and silly things like that. But that did not come to pass, but I did hear it proposed. So, what is Foyle going to be? It's going to be the same as our propositional separate and conquer method, but with two key differences. What are those two key differences? Well, think about the following. What we did when we were doing propositional induction was we look at all the possible antecedents, right? We try adding each one and then see which one works best, right? But we can still do that here. What has changed, though, is the language of antecedents that I can add, right? The antecedents that I had before were just tests like it's sunny today or it's not sunny. The humidity is above 70% or it's not. Now I have a much richer language of things that I could add. In particular, I have, predicates like has word and links from and whatnot. Okay? So that basic idea of constructing rules one antecedent at a time can stay the same. What has changed is that now I have a much more powerful language of antecedents to add. Okay? Everybody got this? Okay, so that's rule number one. I'm going to have to look at different candidate specializations of my rules. In particular, my specializations are going to be what are called literals in logic. A literal is either a predicate with arguments like this or a negated predicate with arguments like this. So these are the kinds of things that we're going to be looking at adding. Difference number one. Difference number two is that obviously I'm going to need a different evaluation function now. Right? Remember, in any learning algorithm, the choice of evaluation function is always one of the key things. And the type of evaluation function that I had before doesn't really work here anymore. Right? Let's suppose that evaluation function was just the accuracy, right? The accuracy was the fraction of correct examples that I covered, right? What is the accuracy in this case? Actually, what is an example in this case? It's not even clear what's an example anymore, right? Before, an example was like, a patient and their 10 symptoms. But now what I have is like this big network, it's the web, there's links, there's substructure in the page, there's tags, what is an example, right? It's not actually clear what an example is and whether it's the same before and after I add an antecedent to the rule. So clearly, as much as we still want to maximize accuracy or information gain or any of those things, coverage, etc., we're going to have to adapt that. Okay? So these are the two changes that we're going to have to make. So let's see how we're going to do that. So first of all, and it's going to be easier than it seems. That's the good news. On the other hand, fair warning, I'm going to gloss over a lot of subtle details here. You're welcome to look at them more in the book and then, for example, look at Foyle and play with it and whatnot. But at a high level, actually, it's not going to be that complicated, at least compared to the part that we're going to get. So, first of all, how do we specialize rules in Foyle? Well, let's say we have this current rule, right? Now notice that for a start, the head of my rule is no longer just a class. It's an actual predicate, like ancestor xy, right? So it's going to be a predicate symbol, p, with some set of arguments, x1, x2, x3, x4, as an antecedent x1, x2, and so forth, okay? And let's say that so far, I have a bunch of literals, L1 to Ln, right? And L1 is really standing for a predicate symbol with a bunch of arguments in parentheses, like, parent xy, or, has link, A, B, and whatnot. Okay? So I have this rule like this so far. Now, what am I going to add to it? Okay? Over to you. What should I consider adding? Oh, and by the way, what is the training set now? The training set used to be, very important point, right? The training set used to just be a table of my examples, right? For each patient, their symptoms, or for each email that words appear on it. What is our training set now? It's actually, again, a much more general thing than we had before. What is a training set for a first-order rule learner?
Graph. That's
one way to look at it, yeah. It can be a graph. Now, we're going to see an example like that in a little bit. It's actually even more general than a graph. But a training data set is going to have instances of this predicate, right? Because we're trying to learn it. Like, it's going to have instances of like, oh yes, Anna is a parent of Bob, and Bob is a parent of, Charles, and so on and so forth, right? So it's going to have a bunch of stuff like that, but it's also going to have a bunch of stuff like this, right? Other relations like, has, word, and links to. So what is this looking like?
Declarations.
Yes, they are. This is declarative knowledge, right? It's a bunch of facts, but more specifically, this is a relational database. Our training set now is a relational database, right? P is one relation, L1 is another relation, right? There's the links to relation, there's the has words relation. Those only had 2 arguments, but I could have a relation here with, any number that I want. Okay? So when we're doing relational learning, this is often called relational learning, what we have is not just a table anymore, it's a whole bunch of tables, meaning a database. Okay? Which is nice considering that, like most of the world's information systems run on databases, and we would like to be able to learn over those. Well, we're about to see how. Okay? So my data is a database, right? And so I have different relations in that database, like the has relation, the has word relation, the links to relation, etc., etc. Right? And I'm trying to build a rule out of those relations. Okay? And let's say I have a rule in which I already have a bunch of those. What is the next thing that I can add? Let's suppose, for example, that in my database, I'm trying to predict P of xy, and I also have something like, rxy, sxy, and t of xy, right? So my database consists of 4 binary relations. Again, they could have many arguments, but for simplicity, they just have 2, right? And I'm trying to learn to predict P as a function of r, s, and t. Okay? So let's say that in my rule, I already have something like, very trivial, P of xy if r of xy, right? What can I add now? What are the first obvious choices? Right, just give me one suggestion of something I might add to the rule.
Negate it.
No, yeah, sure. So that's one thing. I could have something like not xy. But actually, I probably want to have both rxy and not xy. So certainly we want to allow negations of these things. That was in fact my last point. But for the moment, let's ignore negation, right? And say, I'm saying P of xy if r of xy. And I'm going to try to further refine this rule. How might I refine it?
Or s of xy?
Yeah, exactly. I could add one of the remaining ones, right? I could now make it, r of xy and s of xy, or r of xy and t of xy, right? And let's suppose that I just did that, and now I can try the remaining one, right? So now I have P of x1 if r of xy, xy if r of xy, and s of xy and t of xy. And now comes the really interesting part. Am I done with the things that I can add here? Certainly if this was propositional rule induction, I would be done, right? I have now used up all the attributes that I have. But in this case, am I done? Let's think back to the web example, right? Am I done once I have added my, has word and my link from? Clearly not, right? I can keep adding more of those, right? What is the thing that can happen here that couldn't happen in propositional rule induction? I can have the same predicate repeated, right? But what changed from one case to the other? The arguments, right? That's the key, that thing that makes this powerful, is that my predicates now have arguments. And they could share arguments in very interesting and complicated ways. I could add the same predicate multiple times. I say like, this page links to this page that says this, and to that page that says that, and is linked to by another page, and I could even follow another link from one of these pages and go to the words that are 2 steps away. There's all these things I can do. Okay? So the moral of the story is, I don't just have a choice of which predicates to add. I have a choice of which predicates to add with which arguments. Okay? So now another question is, should I just allow any addition of arguments any way that I want? Right, that's the natural thing to say, right? That's my language. Add any predicate within your argument. So for example, I could have P of xy if R of xy, right? And, S of yz, right? This is a perfectly legitimate rule, right? So this is a good thing. But let me give you another example that hopefully will make you think. What about the following? P of xy, R of xy, S of uv. You like this one?
It is surprising.
Sorry.
It is surprising.
Yes, this rule is surprising, right? But more to the point indeed. More to the point. Is it a good idea to add SUV to this rule?
It doesn't have anything or any relation to the original predicate.
That's right. It fails the common sense test, right? I'm trying to classify X, right? Why am I talking about the relationship between U and V that have no known relationship to X? It doesn't make any sense, right? So we probably want to allow this, but not this. Okay? On the other hand, notice the following interesting fact here, right? Is that this, I did have here in this rule that we agreed was reasonable, a variable that never appeared before. I'm allowing this rule to involve objects that I never talked about before. So it's not that I only want my rules to have X and Y in them, right? That would be too restricted. And again, notice that in this example, right, my rule, here winds up talking about, B and C that, did not show up here, right? And also, remember in our ancestor example, there's a key role being played here by Z, right? Z is this person in the middle that X is a parent of and who is then an ancestor of Y, right? So I want to allow that. So, can you induce from these examples what the general rule for what we want to allow is? I want to allow adding any antecedent with any arguments, provided that
It's previously used.
exactly at least one argument already appears in the rule. Doesn't have to be in the head, but it's in the rule. If that argument already appears in the rule, that means that there's a connection between what I'm now saying and what I was saying before, right? I can bring in a new page because it has a link to a page that was related to what I was what I want to classify. And then once I have that page, now I could go look for links to that page, right? What I probably don't want to do is just bring in random pages that aren't linked to any of the pages that I'm talking about already. Okay?
So it's just from a relational database standpoint, it's just like doing a join.
Precisely. In fact, this is exactly what happens. If you want to do this stuff on this kind of large scale, you're going to do it by database joins. And this is all that's going on here, is that this is really what a data log rule is, right? And that's why this really can be used to do queries in databases. If you think of this as a database query, right, what happens is that here, right, there's a non-trivial join between these two things, right? And here, these things don't join, right? They have no arguments in common. Okay? They're talking about different things. Okay? So this is the important point number one, is that I will allow in my language any antecedent, any literal with any arguments with the condition that I have to have at least one argument that appeared before. Otherwise, it doesn't make sense. Okay? This is number one. Number two is something that might seem a little odd at first sight, but actually is quite important, and that's why it's there. I'm going to allow the special predicate equal. Equal xj, xk means that these two variables are the same. So I could actually just replace them both by y. Okay? Now, why would I want to allow that? Versus not just if x, j, and xk are both going to be y, well, why didn't I just call them y to start with? Why would I want to have this here? And let me give you a hint. This is not because of the representation. It has to do with the fact that we're going to learn these things using search that is necessarily greedy. So what might be the advantage of having this in there? Let me put it this way. Suppose that we already have this rule, right? And these rules all have their different arguments. What could be the advantage of adding an antecedent like equal xi xj? What is it doing, right? It's basically saying that these two arguments that I had over here are actually the same, right? Why might I want to do that?
You could just skip the computation if you already know the output for j. You just say if whatever j had, the same thing applies to k.
It might went back, right, when I added these literals, right, it might not have been apparent at the point that at the end of the day these arguments should be the same. Right? I don't want and this as I said is going to happen very often, right? I'm adding a bunch of things, right? And then I realize, well, actually this part here really should be talking about the same thing as this part here. Right? And if I don't allow this equality, at that point I'm host. You could also say that instead of allowing equality, you should allow at some point replacing, different arguments by the same. But the point is that often you want to do this later in the search, in the beginning, when you were adding things greedily. Remember, they were just tied to the existing group by one argument. But now if they have other connections among their arguments, right, that may only have become apparent once I add, the other things that come around to this. So it can be very important to allow equality. It can also be very important to allow the negation of equality. Just as we want to allow the other predicates to be negated, often the most interesting rule is when these things are not the same, because when they're the same, it's sort of like a trivial special case. Okay? So I also want to allow not equals. Okay? Questions so far? We just covered a lot of ground here. So now we know how to build a very powerful class of rules, but we still don't know how to evaluate our candidates. Okay, let's go by what we had before, right? We had this heuristic that minimized, that maximized my gain in surprise, i.e. minimized my surprise, inside the rule, right? And then we also multiplied by, the coverage of the rule, because we didn't want it to over-specialize, right? Let's do that here and see what breaks, and then how to fix it, right? So what happens, so remember, let's say that my rule is R, right? My rule so far is R, and L is the literal that I'm considering adding to the rule. Okay? And now let's P0 be the number of positive bindings of the rule. What is this thing called binding, right? What is the binding of a rule? We didn't have this before. This has to do with the fact that now, what is an example is no longer very well defined. Right? I just, think of this as a graph, right? I have a very big graph of things. And now what exactly is the subgraph that I'm going to use for this particular, prediction? Well, that could vary. What determines the relevant subgraph is the rule, right? It's the things that the rule binds to. Binding is actually the technical term, right? I have a rule with these variables, right? And anything that those variables could be replaced to creates a binding of the rule. I have, a rule about, parent xy, and I could bind that to parent and above, right? So I can have a particular family, and the rule applies to that family with its relationships. That's what a binding is. Okay? So I no longer have a notion of an example. I have a notion of the bindings of the rules. You could say that in some sense all I have is one big interconnected mega example, but that's too much of a headache. Let's just look at the part of that big graph that matches the rule. That's the binding. Well, in general, if the rule is good, it'll match many different subgraphs, right? It'll match this family and that family and that family, right? And that's the number of bindings that I want to count. This is what now plays the role of my number of examples. Now, of course, some of those bindings will be positive, and some of those bindings will be negative. Think of the binding of the rule as a set of people, right? And their relations. In some of those sets, A really will be the ancestor of B, or an ancestor of B, and some of them it won't. The first will be positive examples, and the second will be negative examples. Right? This is a very important notion. Everybody on the same page? Okay, very good. So, I'm going to count the number of positive and negative bindings of the rule before I add the antecedent. Those are called P0 and N0. Okay? And now the surprise of applying the rule before that is log, minus log of P0 over P0 plus N0, right? That hasn't changed. Once we have defined what that rule actually applies to, we can apply our, existing notion of surprise. Okay? And same thing after we add the antecedent, right? Now we've added the new literal to the rule, right? So now there's a new set of bindings, and P1 is the number of those bindings that are positive, and 1 is the number of those bindings that are negative. Remember, let's say I'm building a rule for ancestor, right? In the beginning, that rule is only about two people, X and Y. But once I bring in that third person that you're an ancestor of, and then they're an ancestor of blah, blah, right? Now this rule binds triples of people. The rule used to apply only to pairs of people, but now it applies to triples of people. Okay, big difference. Notice we're in a whole different world from our good old propositional rule induction. Now there's much more going on now. It's much more powerful. It's also more complicated. Okay. So now again, some of those bindings will be positive. In some of those cases, the ancestor relation does hold between X and Y, with that Z or some of those Z's, and in others it doesn't. So now I'm going to have P1 and N1. And I have my new surprise. Okay? But now, first of all, I have the same problem that I had before, that I don't want to have a very specialized rule that has very low surprise just because it doesn't cover anything, right? So I'm going to need something over here, as I had before. But there's an even bigger problem here, right? Which is, we're really, if you think about it, comparing apples and oranges when we compare these two things. Because we may be binding different sets of examples. Again, in the propositional case, this could not happen. Right? But in one case, we're talking about pairs of people, and in another case, we're talking about triplets of people. Right? And the nasty little effect that this can have is that, remember, the basic heuristic that we're using here to be confident of our rule is that it covers a lot of examples. Right? Once it covers few examples, we get suspicious. Because remember, what happened in propositional rule induction is that as I added more literals, the number of examples always went down. At best, it stayed the same, but adding more antecedents meant the example, I was going to cover fewer examples. What happens in this case when I add more antecedents? Does the number of examples always go down? No, in fact, it could go up by leaps and bounds. Let's suppose that I had 10 people in my data set, right? The first rule matched 100, and the new one matches 1,000. Wow, I just got an order of magnitude increase in the number of examples that match my rule for free, right? Clearly, if we don't do something about this, we're going to get all sorts of garbage, out of our rule induction system. So what is the simple thing that we can do here that, at least heuristically fixes this? It's a very simple idea, one of the things, that Quinlan is very good at is coming up with simple heuristics that do the job, and this is a very nice example of that. He's just going to make a very minimal change to what this part here of the heuristic means. And that changes the following, is that this T here is going to be the number of positive bindings of the original rule that are also covered by the new rule. This is going to disallow cheating by multiplying the number of examples by having new bindings. If you think about it, I really only care about the bindings of the old rule. The new variables that I brought in are auxiliaries to help me predict what I really care about, which is whether this is a course page or whether these two people have a family relation like ancestor. Okay? So by doing this, we focus on what we really want, right? I might have multiplied things by a lot. I don't care. I care about which of the old rule bindings are still bound by the new rule. This is actually not obvious, but after you see the idea, it's actually, this at least should work. And again, heuristically works very well, and FOIL is very widely used. Any questions? Okay, so that's FOIL for you, or at least the basics of FOIL. Of course, the full FOIL system has many bells and whistles, and there are many issues in this type of relational learning that we're not going to deal with. Here's just an example for you to think about during the break, or at home tonight, right? Here's a very simple example, just to make things concrete, right? Because we've talked about a lot of very abstract things so far. Let's make it concrete. Here's a graph, right? The simplest interesting example of a problem where relational learning gives you power that propositional learning didn't give you is a graph. So here's a very simple graph. These are nodes in my graph. They represent whatever entities you want, and arrows just represent the relation I'm linked to, right? So let's just say this is a very small segment of the web, okay? And if I were to represent this as a database, it would be a database like links 202, links 201, and so on, okay? So this is my data, okay? And now let's say that what I want to learn is the concept of can reach. Can reach x, y means that I can reach y from x by following the arrows. So for example, can I reach 3 from 0?
Oh, yes.
Yes, right? Because by way of who? 1 and 2, right? Can I reach 0 from 3? No, because I have to go against the arrows, okay? So I have a database of links, and I want to introduce the concept of can reach, right? Simple example. So my data is, first of all, it's my pairs of nodes, right? And then whether, for each one of them, whether they link to or whether they don't link to, right? Sometimes we leave the not implicit, sometimes we make it explicit, right? This is what's called the closed world assumption in databases, right? Closed world assumption means that everything that is not in my database is assumed false. So with the closed world assumption, I wouldn't need to say this, but let's just suppose for clarity that I do say this. The downside of saying it, of course, is that a lot of time, imagine a database of flights that have, all the pairs of cities that don't have a flight between them, right? That would be really inefficient, right? But in the simple example, let's suppose that you actually have that. And by the way, FOIL allows both of them, okay? And the corresponding adjustments of the evaluation criteria. So now what are the hypotheses that I'm going to make, right? They're going to be rules that have can reach as the consequent, right? This is what I'm trying to predict, right? And what can they have in the antecedent? What literals can they have? Or what predicates can appear? Right, so I'm trying to predict can reach using what?
X, Y, and can reach. Sorry, X, Y, and link to.
Right, so I'm trying to predict can reach from link to, right? I can reach A from B if A is linked to something and something is linked to B, right? So I'm going to try to build rules that predict can reach in terms of link to. Anything else? Think back to the ancestor example, right? Shall we? Well, let me put it back up, right? I was predicting ancestor in terms of what? Parent, yeah, and what else? Ancestor itself. That's the fun part of this. It's the recursive rule, right? As always, there's a lot of power in recursion, right? Again, in the propositional case, this made no sense whatsoever. I can't predict a class in terms of itself. But now, because it's the predicate with different arguments, right, I can predict ancestor xy in terms of ancestor zy, right? So, in our can reach example, I want to predict can reach in terms of what? Length to and can reach. In fact, you've probably already noticed that there's something of an isomorphism between this problem and the family problem, right? What is the analog of link to here?
Relative.
Parent, right? And the analog of can reach is ancestor, right? And in fact, you can squint at a lot of different, network data sets, social networks, right? There's, the friends relation, right? The famous social graph, friends XY. And, friends of friends are friends and all of that good stuff, right? You can represent it all this way and learn the corresponding rules. I don't know if Facebook is using this technology yet, but, but maybe they will if they're not. So our hypothesis space is that we want to learn rules, also learn as horn clauses, using the predicates linked to and can reach. Okay? And so the exercise for you, which at this point is probably not very difficult at a high level, is figure out what would be learned by FOIL and also how. Right? You can probably figure out very quickly at this point how, what needs to be learned here. But the question for you is how would FOIL arrive at this? And also, what might be some of the difficulties and where do FOIL's heuristics come in handy? Okay? But in the meantime, we should have a break. It's 8:06, so let's reconvene at 8:16, where we will look at the second major type of first-order rule induction.